So when I tell about a perceptron model, you really have to understand that, okay, how does these weights vary? How does these inputs, based on the inputs, how my weights vary? This is how even your gradient descent algorithm works. See, this is a very simple example. It's a very, very simple example with respect to an AND gate where I have only 4 values of it, okay? So 2 cross 2, okay? 2 inputs, so 2 cross 2, I have 4 values for that. That's it. But consider a non-linearly separable data. You have huge, and I have to now transform that in the different domain. From a 2-dimensional, now I convert into a 3-dimensional. Now I'll be getting something like this. Okay, I have these values over here. Just you have to imagine it. Okay, so imagine yourself that there is a far away you have a set of chunk of data, and here very near to you have a chunk of data. Now you have to differentiate or categorize them. So you have in between some of the data. Okay, so it's always not equal. It's always going to be overlapping data. So now I have all of those data in between like this. Now how do I actually get to know a separation? I have to create something, a separation between these two, classifying them. So what it does is add behind, okay? First what it will start is, it will take all the input values of this. It will take the input values of this as well, okay? Each and every time it will start learning. So what the first time what it will do is, okay, suppose let me create a plane now, okay? So it's gonna classify it, okay? I'm just trying to give you an example, okay? You can consider the normal SVM also for this, okay? So when I tell the non-linear separable data, first what it will do is, it will put a line like this. So a line in where I have some data chunks here, okay? I have some data chunks here, and in between also there are a few small. Okay, first time what it will do is, it will come here. The classification accuracy was for that was very less. Like it did not give a correct value. There were some misclassified values for that. So now what will my system do? It will identify the difference between them. Now the same way, how did you do it over here? Expected value and the target value. It will consider the expected and the target value for that corresponding input instances. Wherever misclassification has happened, it will take only those values. It will not take all the values. Wherever misclassification has happened, 0 and 1, it will take that value. From there, it will start considering, okay, now what is the input corresponding to that and the weight value of it, what weight value I should update. Now it updates, and next time it was like this, right? It will come still more farther to you. Okay, there is a change that happens. So now from here to here, it has gone. Again, what it will do, it will again check, okay, there are some more misclassified data in it. There is a loss function. So once the loss function, what does loss function mean? It means it has to update its weights. Loss function, when I tell loss function, it means it has to change its weights. So changing its weights is basically target minus. So it will consider the difference of it and its corresponding input value. Again, it will change. So now, suppose I will tell this is where I get a classification accuracy of at least 99% or 97%. It's very close to you. Initially, it was here. Now we are moving, you're changing, you're finding out, you just go like this, like that, like this. So I will come directly to one particular point, my local minima, where I identify that this is what my correct classification is. So that changes whatever would have been done, right? That is what an update to your weight that happens. You can see here also, as and how I change these weights, my line, my linear regression line actually came up to the correct classification. Okay, so this is how the background knowledge of it works. Let me just show you the theoretical part of it. Okay, so what is the gradient descent, and give me 1 minute. Yeah, so we already saw this, right? Error in the training error, the hypothesis, the weight, what was it? The error is basically my loss function. My loss function, when I tell, is basically target minus of the output, the whole square, the mean square error. I can have the cross entropy loss function as well. So any loss function that I consider is basically gives my training error. My intention now is I have to reduce the loss function of it. How do I reduce the loss function? So when I tell I have to reduce the loss function, reduce the gradient descent. Okay, when I tell I have to have a gradient descent, what does gradient descent mean? To just give you a clear picture about it, what gradient descent is, whenever tell, okay, I am going to update a weight to it. Okay, so when I tell I have a loss function, okay, loss function is basically my output comma predictor. So this is my loss function, right? So when I tell this is my loss function, I have to update the weights. right? Updating the weights, how do I do it? I have to consider the loss function with respect to that weight, right? So what I do over here, I'm just calling that derivation of this gradient descent. I have to actually find out the steepest descent along the error space. Steepest descent is, see, I have in a graph when I consider like this, right? The steepest descent. This is what completely it will tell me. My learning rate should go, my loss function should go like this, the steepest one. Okay, so when I tell my loss function is going very low, which means that I need not update more of my weights. When my loss function is going like this, which means that the target and the output value is almost same. Both of the values 50 lakhs and 30 lakhs, now I'm increasing its weights, it's almost coming to 50 lakhs itself, which means that my loss function is very less, it's going very low, and I need not, I've come up to the accurate weights, right? I've come up to the accurate weights. So basically that loss function, I'm going to write it as the delta gradient of E. Okay, I'm going to tell that, okay, computing the derivation of E with respect to each component vector, the weight, I call it to be as gradient of E, such that delta E of W is equal to the loss function with respect to W1. What I tell loss function in the sense, I have to get a minimal value. To get a minimal value, what I do, I take those two values, I apply it onto the input instances, which gives me my weight, right? This is what the logic is. Each and every weight update, when I do it, it's going to take the difference of it, apply onto it, and I'll get the weights. To do so, I have to apply this loss function on each and every weight, right? So that is what I'm going to derive over here. So I'm going to derive here telling that so delta E of delta W0, loss function with weight 1, loss function with weight 2, loss function so on up to weight n. Okay. And here it tells me like, see, when I tell loss function, when it goes very low, which means that I have to update my weights, right? So I want you to keep in mind that when I tell gradient descent, right? Gradient descent, the opposite value of the gradient descent is nothing but the loss function with respect to the weights. Okay. So this gradient descent, whatever I consider, is always gonna be in the opposite direction of the weights. Which means that whenever I tell gradient descent, see, because you have to visualize, it's something, a terminology where I want my target value and my predicted value to be less, which means that my loss function should be less. In order to make sure my loss function is less, I have to update my weights. So gradient descent is nothing but, so I want this function to go low, right? And I want my weight to be updated. It can be minus or plus, but I want it to be updated corresponding to the direction which is negative to gradient descent. If my gradient descent is going low, obviously my weights will be increasing. If my gradient descent is going high, which means it's always opposite. The directions of gradient descent and the weights are always opposite. It's a negation of it. Okay, so when interpreted as a vector in weight space, this is all an imagination part that you really have to consider. The gradient specifies the direction that produces the steepest increase in E. Increase in E, you can consider gradient specifies the direction that produces the steepest increase in E. Increase in the E in the sense loss function. This error that I'm talking, right? Increase in E is it should go low. The way it is interpreted is like as I told you, AC high, AC low. So you have to get a curve like this. So I want, my intention is I have to get a lower curve. That's it. But to get that, the negation of this vector, whatever I consider, gives the direction of the steepest decrease. The negation of this. So, okay, if you are even finding this confusing, keep only one thing in mind. For me, my gradient descent or my loss function should become low. In order to perform that, I will be going in the direction opposite to gradient descent. So which means I'll be updating my weights such that it is opposite to the gradient descent. You just have this at least in your mind so that it does not make you more confusing. When I tell I want to decrease this value, so when I'm decreasing the loss function of it, which means I'm going to go ahead with the gradient descent considering it. So that value of it is going to be opposite. The negation of it is where I'll be applying to my weights. Okay. So the training rule, we know W bar is W bar plus delta Wi. So W new is equal to W old plus delta Wi. Where delta Wi is, you can see it's going to go in the negation part of it. Move in the direction opposite to E. Wherever I'm considering the loss function with respect to the weights, I am going to move in the opposite direction for that along with the learning rate. This is what means gradient descent, and the delta rule is this. Go in the direction opposite to. Okay. So now I'll start doing the weights. So it's basically Wi is Wi plus delta Wi. I already know. I'll start the derivation of it now. Derivation of it, and this delta Wi is what I've got it over here. I'm writing it as delta E divided by delta Wi. So delta E divided by delta W0, delta E by W1, E by W2, so on up to Wn. Because this is what the loss function I'm going to do with each and every weights. I'm applying to each and every weights. So to apply that, I take the learning rate and the negation. To start the derivation, I know this is my loss function. Okay, TD minus of OD the whole square 1 by 2. This is my training error. From the training error, I start solving the derivation to get the above equation. How do I do it? 1 by 2 into summation of d by, I'll just take this term like this. I'm going to take the partial derivative with respect to the weights of this. So something with partial derivative of x square partial derivative, okay, divided by dx x square, okay, is equal to 2x into delta x. This is what it is, 2x into delta x. So what I'm doing, I'm taking this 2x, I'm writing 2x into delta x. The same, whatever this partial derivative, I'm applying it onto this and I get that value. Okay, and this 2 half gets cancelled. Now what I'm doing here is I keep this term the same, but OD, we already know the output, perceptron model, the output is equal to W bar into X bar. The output value, if you remember this O of D from the perceptron module is weights into the that is the weights into the input instances, W into X. So I'm going to write that over here. Now what happens, I'm taking the partial derivative of this. Partial derivative of Wi, there is no term dependent on Wi over here, so I'll neglect this. But there is a dependent term with respect to W over here. So what I do, delta of something with respect to delta X over here is basically, I'm going to write it as like, suppose I have 1 into X, I'll just get value of 1. If I have 2 into X, I'll get a value 2. Somewhere here I have this value, whatever, this is the X value, and whatever the value over here is what I put it over here. So I'm going to take X as minus because there's a minus sign over here. I'll take that value over here, the constant value, which was with respect to the weights. I have that value. I will finally get this value. Now let me consider, I'll just substitute this value in this equation. So it's going to be delta Wi is equal to minus of learning rate into TD minus of OD into Xi. This was the same perceptron training rule that we take up. But the perceptron, one clear difference is that you really have to identify here is the perceptron training rule, it was a positive value. Your perceptron training rule, it was a positive value here because it was a linear data. But now it's a non-linear separable data where I have a gradient descent that's coming into picture, which means that, as I told, however the weights move, it is in the three-dimensional view. The weights that whatever I considered was in the three-dimensional view. And from the three-dimensional view, we will get to know whether it is coming to the local minima or not. In order to do so, it's going to be opposite to the gradient descent. Okay, opposite to the gradient descent the direction in which it will go, it's going to be opposite to the gradient descent. So my weights is going to take minus of the gradient descent value. That's the weight value. It goes in the opposite direction of it. So I'll be writing it minus over here. It's the same equation, perceptron training rule, but perceptron training rule with the gradient descent is different. With gradient descent, it is always opposite to the direction of the gradient descent. So I'll get a minus sign for that. I will be updating it as minus learning rate into the same equation. This is what your gradient descent is. To elaborate this concept, it might look very, very like you have to imagine a lot with respect to this concept. Only then you can come to a converging solution. Probably I'll be taking up this example again on a simulation model. So I'll make it more in detail about this. I'll again elaborate the same concept with the simulation model in the next class. That's in the tomorrow's class. Okay, I'll give you the similar simulation model that I was talking to you about. I will incorporate even this part to give you more idea on, okay, how does this look? How are we updating the weights each and every neuron? How is the gradient descent calculated? So I'll let you know all of these. Okay, if you have any doubts, you can let me know.